Thank you very much, fellow Kenyans. I'm Honorable Babu Owino, Member of Parliament in Embakasi's constituency and your teacher. Today we have Chemistry KCSE Revision, a topic called nitrogen and its compounds, which will be covered by Mr. Thaddeus Mbaluka, who is very familiar to you. I hope you will suckle from the nipples of his wisdom. Stay tuned and enjoy. Thank you.
Okay, asante sana Mheshimiwa Babu Owino for this opportunity to interact with the Kenyan students in this time of COVID-19 as we try to provide the best for the learners. I am teacher Thaddeus Mbaluka, and I'm going to teach you Chemistry Form 3. Our topic of interest today is nitrogen and its compound, and the subtopic is ammonia. In our today's lesson, we are going to be dealing with the laboratory preparation of ammonia. Welcome. We'll start by looking at the lesson objectives. By the end of the lesson today, you, the learner, should be able to describe the laboratory preparation of ammonia. You should be able to describe a chemical test for ammonia, and you should also be able to state the physical properties of ammonia gas. We start by looking at now the reagent that you use. Ammonia is prepared in the lab by heating a mixture. Ammonia is prepared in the lab by heating a mixture of ammonium salt with a base. Ammonia is prepared in the lab by heating a mixture of ammonium salt and a base. The base we can use here, there are three alkalis we can use, or rather there are three types of bases that we can use in this kind of reaction. One of them is calcium hydroxide. We can use calcium hydroxide. That is one of it. We can also use potassium hydroxide, and we can even use sodium hydroxide. So those are the three bases that we can use. We have the potassium hydroxide, we have the calcium hydroxide, and we have the sodium hydroxide. Those are the three bases that we can use in this reaction. When this reaction is taking place, the anion, like here we have ammonium chloride reacting with calcium hydroxide. So the anion from the ammonium salt, like here in this case we have chloride, will react with the cation, of the base, that is calcium, to form the calcium chloride. The remaining component, that is the ammonium component combined with the hydroxide component of the base to form water and ammonia. Very simple. Wherever you are having this kind of a reaction, the anion component of the ammonium salt will combine with the cation component to form the corresponding salt. So the anion component in ammonium chloride is chloride ions, will react with the cation component of the base, that is the calcium, to form the calcium chloride. The remaining component, that is the ammonium, and the hydroxide ions react to form the water and ammonia gas. Let's look at the other reaction. We are having the ammonium sulphate reacting with sodium hydroxide. We start by looking at the anion component of the ammonium salt, the sulphate ions, will combine with the cation component, which is the sodium, to form the sodium sulphate. The remaining component The remaining component, that is the hydroxide ions, will combine with the ammonium ions to form ammonia gas and water. That is how it is easy to be able to get that point. Remember, in preparation of a gas, you need to know the reagents. You also need to know the condition that is required for this particular kind of a reaction to take place. And for this reaction to take place, heating is necessary. So in all these, you require some heat. Some heat is necessary. Make sure that you are able to know that. Another thing, the reagents must be dry, solid. The reagents must be in solid state. The reagents. None of the reagent is aqueous. They must be in solid state. Very important for you to be able to capture that. We now look at the diagram, the experimental setup that is used in manufacture of ammonia in the laboratory. We are looking at, in the diagram, I'm using ammonium chloride and calcium hydroxide. Remember what I said? They must be in solid state. They must be dry. The key word here is they must be dry. The reagent must be dry. The orientation of the round-bottomed flask is that it must be slanting and should be slanting downwards. It should be slanting downwards. The round bottomed flask must be slanting downwards. There are some common mistakes with most of the students whereby they write the flask should be slanting. That is a complete misnomer. It is a misleading statement. It has no scientific meaning. Scientists are precise and they are very specific. So when you talk about slanting, you tell us it should be slanting downwards. An apparatus, you can look at this. You can have a flask like this, slanting, but it is slanting upwards. So the thing that you need to look at there is the flask should be slanting downwards to prevent the water vapor formed from condensing and flowing back to the flask. Remember that we are saying the water vapor, when you refer to the previous slide, water is one of the reagents. Therefore, when you are preparing this water will be formed in form of water vapor because of the heat that is involved. Therefore, if the flask does not slant downwards, then the water will condense and flow back, causing the flask to break, or rather to crack. Then the gas, once has been prepared, it is directed toward the drying tower, the dryer, whereby you find the drying agent is calcium oxide. Calcium oxide is the only drying agent that is used to dry ammonia. Ammonia cannot be dried using concentrated sulfuric acid, neither can it be dried using fused calcium chloride. Why? Because ammonia will react with both fused calcium chloride and concentrated sulfuric acid. Very important to be able to capture that point. Remember the properties of a drying agent. It should never react with the gas that is being prepared. And ammonia is collected by upward delivery because it is less denser than air. Ammonia should be collected by upward delivery because it is less denser than air. We continue. And we look at the commonly used base, as you have seen in my diagram. Although I told you that we can prepare our ammonia using both calcium hydroxide, potassium, or sodium hydroxide, in my diagram, I've used ammonium chloride and calcium hydroxide. The rationale, why do we preferably always use the calcium hydroxide and ammonium chloride? Because the calcium hydroxide is readily available and it is cheap. Rather, it is cheaper. That's the even, it is cheap, or rather cheaper than the other bases that are used. We also have ammonium chloride, is also most commonly used because, again, it's also cheap and readily available. Let's look at the test for ammonia. You dip a glass rod into concentrated hydrochloric acid solution and lower it into a gas jar full of ammonia. It will form white fumes. It will be able to form white fumes. So whatever we are saying here is, when you have ammonia and this ammonia gas is brought in contact with hydrogen chloride, then you get ammonium chloride, which appears as white fumes. It appears as white fumes, or it can also appear as a white solid. On cooling, it is solidified, forming a white solid. It's also important to understand that a very important point to note is that ammonia turns a red litmus. Ammonia will turn a red litmus paper blue. Ammonia turns a red litmus paper blue, meaning that it is alkaline. Ammonia is the only alkaline gas that you're going to interact with. Although ammonia, when you test ammonia as a red litmus paper, it turns a red litmus paper blue, indicating that it is alkaline, or rather it is basic. We don't take it as the chemical test for ammonia. The conventional test that has been accepted, or rather approved by the UPAC, that is the International Union of Pure and Applied Chemistry, is the one of exposing the ammonia gas to hydrogen chloride gas, whereby you're going to get white fumes. So, but remember again, if you also find a scenario whereby a gas is turning a red litmus paper blue, then that gas is automatically going to be ammonia. We continue. Note, in preparation of ammonia, as I captured there, that the round bottom flask should be slanting downwards, left to right, to prevent the water vapor formed from condensing and flowing back to the flask. So the round bottom flask should be slanting downwards, left to right. This to prevent the water vapor produced from condensing and flowing back to the flask, which may crack it. Common mistake students will talk about the water condensing. A student might write water condenses. this is not chemistry. It is something else. Once the student completes research to the water condenses, then automatically it goes against. When you say water condenses, it negates and contradicts the concept of condensation. Water is a liquid, it cannot condense. Whatever is condensing is water vapor. Very important for you to be able to capture that. Most reactants should not be used. Most reactants should not be used because ammonia is, this will dissolve the ammonia gas produced. Ammonia is very soluble, it's one of the highly soluble gases ever known. So we cannot use a moist reagent, and that is a precaution. That wherever you are even setting up the apparatus must be dry. And number two, moist reactant should never be used because ammonia, being very soluble, will dissolve in the moisture available. Very important for you to be able to capture that. And remember again, and I repeat, wherever you're talking about the orientation of the round bottom flask, that now the round bottom flask should be slanting downwards to prevent the water vapor produced from condensing and flowing back to the flask, which may cause it to crack. Again, important point to note, the gas is collected by upward delivery. It is less dense than air. There are very few gases that are collected by upward delivery, and that is mostly hydrogen and ammonia. The other gas that is collected by this is hydrogen and ammonia. These are the gas that are comfortably collected by upward delivery because they are purely less dense than air. The other gases are rarely collected by upward delivery because most of them, they, like the carbon dioxide, the oxygen gas, their density is almost close to that of air. Another important point is that the gas is dried by passing through calcium oxide, but not concentrated sulfuric acid or anhydrous calcium chloride, because it reacts with both concentrated sulfuric acid and calcium chloride. Very important. A gas should never be dried using a drying agent which can react with it. So ammonia can react with both fused calcium chloride and concentrated sulfuric acid, and therefore you should never use either anhydrous calcium chloride or concentrated sulfuric acid. Something that I want you to capture is, as a learner, is ammonia is a gas, is the darling of the examiner, because in many times you're going to be asked by the examiner, name the drying agent for ammonia, because ammonia has only one drying agent, that's the calcium oxide. It would be very difficult to find an examiner asking you to give a drying agent for hydrogen. Why? Because the three drying agent can be used to dry ammonia. The other gas that has only one drying agent is hydrogen sulfide. It's important to understand. So these two gases, in terms of their drying agent, is very important. Hydrogen sulfide is a reducing agent. Cannot be dried using concentrated sulfuric acid because it will react with it. On the same note, hydrogen sulfide is acidic and therefore cannot be dried using calcium oxide because calcium oxide is basic and they're going to react. So the only drying agent for hydrogen sulfide is fused calcium chloride. And remember, when you are writing it in an exam, it must be fused calcium chloride. Just to give you something that is very important. I just want to show you something that you can use now that we're talking about gases. The field for the candidates who are waiting for the KCSE, although this is a Form 3 topic, I want to give you a simple rule that you can use. You don't need to, there are 18 gases in the syllabus. And in any exam, there will be between 15 to 20 marks relating to gases. One of the things that we ask students is drying agent. Let me give you a simple rule. All gases can be dried using concentrated sulfuric 6 acid except ammonia. Except ammonia and hydrogen sulfide. So all the other 16 gases, you can dry them using concentrated sulfuric 6 acid except hydrogen sulfide and ammonia. So you don't need to cram the drying agent for the other gases. The same scenario. Fused calcium chloride can dry all gases except the likes of hydrogen sulfide. So like the fused calcium chloride can be used to dry all gases except ammonia. So you see, like the other 17 gases, you can simply use the fused calcium chloride. You can use the fused calcium chloride as long as it's not ammonia gas. So all the other 17 gases, whatever I've said, that conc sulfuric 6 acid can dry all gases except ammonia and hydrogen sulfide. Fused calcium chloride can be used to dry all gases except ammonia. That is a line that you can use in order to revise. Let's continue. And we have said that let's look at the physical properties of ammonia. Let's look at the physical properties of ammonia. So ammonia is colorless. It has a pungent smell. It is less dense than air, and that is why it is collected by upward delivery. It is highly soluble in water, and hence a solution of ammonia is prepared using an inverted funnel. It's highly soluble in water, and hence a solution of ammonia is prepared using an inverted funnel. Very important for you to be able to capture that. Let's look at now the concept of preparation of ammonia solution. Now we have said ammonia is highly soluble in water. So if now you are told to prepare a solution of ammonia, you just set up the experiment as I had shown. And after setting up the experiment as I had shown, now you direct the gas over beaker containing water. And you are using an inverted funnel. So we are using an inverted funnel. So to prevent the role of the inverted funnel, somebody will ask you, what is the role of the inverted funnel? It provides a large surface area for the dissolution of the gas and therefore prevents sucking back. The inverted funnel provides a large surface area for the dissolution of the gas and therefore prevents sucking back. A common trick by the examiner will be identify apparatus B. Common mistake. Examiner will ask you to identify apparatus B. Many students say this is called an inverted funnel. And you get a 0 for that. The name of that apparatus is simply called a funnel. Wherever you are learning about apparatus, there is no apparatus in the lab called an inverted funnel. The same way when it asks you to identify this apparatus A, you don't tell us this one is a slanting round bottom flask. The name of that apparatus is simply called a round bottom flask. So the same scenario here, the name of the apparatus is a funnel, or rather a filter funnel. So those are some of the common mistakes. We only talk about inverted funnel by describing the orientation of that apparatus when we are preparing a solution of ammonia. We are only talking about it when we talk about the solution of ammonia. So in that kind of a scenario, we want you to understand that in case the examiner tells you in case you are asked to identify the apparatus, just say the apparatus is simply called a filter funnel. Very important for you to be able to capture that. And the role of the inverted funnel is to provide a large surface area. is to provide a large surface area for the dissolution of the gas. It to provide a large surface area for the dissolution of the gas. Is to use the role of the inverted funnel is to provide a larger surface area for the dissolution of the gas. Very important for you to be able to understand that. Very important. Now we can continue and we go to the next slide whereby you're going to see the points to note. The purpose of the inverted funnel is to provide a large surface area for the dissolution of the gas, provides a large surface area. The role of the inverted funnel to provide a larger surface area for the dissolution of the gas, and this prevents the sucking back of the water to the hot flask. This inverted funnel is also used to prepare other very soluble gases. Other very soluble gases we have like hydrogen chloride gas. We also have sulfur oxide gas, and we also have nitrogen oxide gas. These gases are highly soluble, and if you want to get a solution of them, then you use an inverted funnel. Then you go to revision exercise from what we have learned. What is likely going to can be asked in the exam. A student set up the apparatus as shown in the diagram below to prepare and collect ammonia gas. Using that, try to get a piece of paper, try to attempt that particular question. The setup is given by the examiner. Identify 2 mistakes in the setup and give a reason for each mistake. Before you answer this particular question, I want to unpack this particular question. You need to know the expectation of the examiner. And what are those expectations of the examiner? You are told to identify 2 mistakes. When you are told to identify the mistakes, what do you look for? What to look for? What to look for? You look for what? You look for the reagent. Could the examiner given the wrong reagent? You also look at the conditions. Like we say, when you are preparing a gas, there could be like heat. There is a catalyst. Maybe the apparatus or rather the reagent should be dry, like the case of ammonia. You also look at the drying agent. Is it correct? You also look at the drying agent. Is it correct? You also look at the method of collection. Method of gas collection. Very important. The reagents we are using ammonium chloride and calcium hydroxide, correct. The reagents are dry. Is that correct? No, we said the reagents are moist, but they should be dry. So that's a mistake. The other one is the drying agent. They have not identified it, so we cannot pick it as a mistake. What is the method of gas collection? You normally collect ammonia using upward delivery, but this one is downward delivery. So again, that is a mistake. Look at the orientation of that flask. It is landing, but it is landing upwards. Another mistake. So whatever now, we have already identified around 3 mistakes, but the examiner wants 2 mistakes and reason for each mistake. So let's start by looking at that. Number 2, because that is where students will fail the exam because they don't know. You set your own exam and you start answering it. When you are told to identify the mistake, don't give the correction. So like the mistake here, the flask is landing upward. That is the mistake. Reason, the water vapor formed will condense and flow back to the flask. A student will come and say, the flask, we say, when we're preparing ammonia, the flask should be slanting downward. So a student will say, the flask is not slanting downward. So that is not a mistake. The mistake is, if it's not landing downwards, what is it? How is it landing? So the mistake is the flask is landing upwards. Reason, the water vapor formed condenses and flows, may condense and flow back to the flask, causing it to break. That is the reason. Number two, wrong method of gas collection. Ammonia is less dense than air, period. So the mistake is wrong method of gas collection, rather collecting the gas by downward delivery is wrong because ammonia is less dense than air. That is how you give your answer. Number three, moist reagent should never be used because the ammonia gas will dissolve. So you see, those are the expectations that we expect from you. So look at my answers. The mistake, the method of gas collection is wrong. Don't tell us the ammonia should be collected by upward delivery. You are giving us the correction. We want you to identify the mistake. The mistake is wrong method of gas collection. Why is it wrong? Because ammonia is less dense than air and therefore cannot be collected by downward delivery. The flask is landing upward. That is the mistake. Reason, because the water vapor, this should be water vapor. Yeah, the water produced, because when you say water produced is correct, water produced may run back and break the flask. That's one way. Or you say the water vapor may condense and flow back to the flask. But when you say water vapor is correct, because by the end of the day, we're still going to form water. So water produced may run back and break the flask. The other part is moist reagent should not be used. Rather, use of moist reagent is wrong. Reason, because the ammonia gas will dissolve. So most of the common mistakes that students write is the ammonia should be collected by upward delivery. That is not a mistake. You are giving us the correction. Another student will say the flask should be slanting downwards. Again, that is the correction, not a mistake. Another common mistake which is captured in most of the books, students will say the flask is not slanting. And as I was telling you, that statement of the flask is not slanting, this flask is slanting, but it is slanting upwards. So make sure that you are able to capture that examination language, which may change the scientific facts. So the other one is the use of moist reagent is wrong because the ammonia gas produced will dissolve. By the end of the lesson, you, the learner, should be able to name the raw materials and the optimum conditions that are required for industrial manufacture of ammonia. You should be able also to state the uses of ammonia gas. So watch until the end. So we look at the industrial manufacture of ammonia. Ammonia is prepared industrially using the ABBA process. You need to be able to know from the specific objective the raw materials, their sources, and the optimum conditions. And when you talk about the optimum conditions, we are talking about the temperature, the pressure, and the catalyst. So the first condition, the first raw material that we require is hydrogen gas. The other one is nitrogen. So where do you get, what is the source of these raw materials? Hydrogen from cracking of alkanes, and nitrogen is from the fractional distillation of air. Very important to be able to capture that. So we look at the conditions, and when you talk about the conditions, you are looking at the following. When you talk about conditions, we talk about temperature, we talk about pressure, we talk about a catalyst. So for industrial processes, we talk about catalyst, we talk about pressure, we talk about temperature. So let's look at the conditions. We require iron catalyst. We require iron catalyst. We also require a pressure of between 200 to 500 atmosphere pressure and a temperature of 450. Usually, the temperature here is between 400 to 500 degrees Celsius. But in a normal examination setup, you are supposed to write a specific temperature. You can talk about 400 degrees Celsius, 450, 500. So for pressure, again, you need to talk about a specific pressure, like a pressure of 200 atmosphere pressure, a pressure of 400, a pressure of 500 atmosphere pressure. Just be give specific, but that is the range of the pressure. So we are saying for this one, the raw material that we need is, we require nitrogen and hydrogen. The hydrogen is obtained from the cracking of alkanes. The nitrogen is obtained from the fractional distillation of liquid air. Very important for you to be able to capture that. The raw materials, we have the iron catalyst. But remember the iron catalyst, here, the iron catalyst here is finely divided. The iron catalyst is finely divided. It is finely divided. It is finely divided. The iron catalyst finely divided, is finely divided, and also it is mixed with aluminum oxide. So we normally say the iron catalyst is finely divided and it is enriched, or rather impregnated with aluminum oxide. There are so many things that you can be asked here, like why should the catalyst be finely divided? To increase the surface area. You can also be asked, what is the role of the aluminum oxide? It acts as a promoter, and promoter is a substance that increases the efficiency of the catalyst. So the aluminum oxide increases the efficiency of the catalyst. Very important. We look at the industrial manufacture of ammonia by the Haber process. You need to have a look at what are the steps followed. The first step is purification. The first step in the first step in this process is purification. So the steps that are involved in industrial manufacture of ammonia by Haber process, the first step is purification to remove impurities. The next step is compression. You compress to increase the pressure of the gases. You heat the gases, which takes place in the heat exchanger. reaction, the main reaction will always occur at the catalytic chamber. The main reaction that is required to form the ammonia, the main product, which is ammonia, it takes place in the catalytic chamber. So make sure that by the end of this particular lesson, you know why do we need to purify, where is the purification done, and which process is used. How do you need to, why do we need to compress the gases, and how do we able to get the required temperature? Because he said we have the specific temperature that we need to attain for this reaction to occur. We have the specific pressure that we need for this reaction to occur, and that's why we are passing the gas through the compressor. We are also heating the gases and also the catalyst. By the time you reach the catalytic chamber, you have attained the required pressure by compressing, and you'll also be able to attain the required temperature in the heat exchanger. And then once you have the correct pressure, the correct temperature, and the correct catalyst, then a reaction takes place to form ammonia gas. So we look at the industrial manufacture of ammonia by other process, and we're looking at the first step. So the first step, as I said, is purification. The nitrogen and hydrogen are first purified to remove impurities. So the impurities there are the dust particles. Remember, you need to know which impurities are removed. So we remove the dust particles and arsenic compounds. They are removed via electrostatic precipitation or by use of filter. So the two processes that are used in removal of impurities, we have the electrostatic precipitation and filtration, which remove the dust particles. They are purified to avoid poisoning the catalyst. The nitrogen and hydrogen are then mixed in the ratio of 1:3 respectively. So we are saying if you have nitrogen reacting with hydrogen, you should have, for every mole, or rather 1 volume of nitrogen, should be reacting with 3 volumes of hydrogen, meaning that if you have 1 liter of nitrogen, react with 3 liters of hydrogen gas. So in this particular point of purification, you need to know which impurities are removed, the dust particles and arsenic compounds. How are they removed? By use of electrostatic precipitation or by the use of filters. What is the main reason why you need to purify? To avoid poisoning the catalyst. Then the nitrogen and the hydrogen are then mixed in the ratio of 1:3 respectively, because somebody can ask you, state the condition that is required at the purifier, and the condition that is required to purify that the nitrogen and hydrogen are mixed in the ratio of 1:3. So a common mistake that students will capture is when they asked why you need to purify the gases, they simply say to remove impurities. That is simply repeating the question. So you purify the gases to avoid poisoning the catalyst, because impurities poison the catalyst. So we continue. The step number 2, we are going to the compressor, that is the compression. After purification, now we have the pure gases now. So here we have the pure gases. The purified gases are compressed to increase the pressure. This because high pressure favors higher yield of ammonia. High pressure favors higher yield of ammonia. So it's important to understand that we have hydrogen reacting with nitrogen. This is a reversible reaction. To form ammonia gas. There are 2 moles of ammonia produced. Here we have 3 moles of hydrogen gas. So these ones, when they are reacting, they form ammonia. Remember, this is a gas. This is also a gas. This is also a gas. As you can be able to see on the side of reactant, we have 3 moles of hydrogen react with 1 mole of nitrogen to form 2 moles of ammonia. The formation of ammonia will be accompanied rather by a decrease in volume, and this is favored by high pressure. So when you increase the pressure, you're going to get higher yield of ammonia when you increase the pressure. So the details of this mechanism, you'll be able to understand it later when you are learning about the dynamic equilibrium. So, but for the Form 4 who are listening here, remember what you talk about. The total volume of the reactor, that is 3, again is 1. So these are 4 volumes, and these are 2 volumes. Increase in pressure for a reversible reaction will favor the side with lesser volume. So the formation of ammonia is accompanied by decrease in pressure, and therefore is accompanied by decrease in volume, and therefore favored by higher pressure, because we say increase in pressure for an equilibrium, rather for a reversible reaction, will favor the less voluminous side. The side with less volume is this, but for the, as I said, for the form produced, the understanding of this concept will be explained further when we'll be dealing with dynamic equilibrium. So we go to the heat exchange, and in the heat exchange, the compressed gases are taken to the heat exchanger. The compressed gases are taken to the heat exchanger, whereby the gases are heated. Now, the gases are heated to attain this temperature, the temperature of between what? 400 degrees Celsius to 500 degrees Celsius. So the role of here is to attain the required temperature, which is 400 to 500 degrees Celsius. That is why we attain this particular temperature, which occurs in the heat exchanger. Very important for you to be able to capture that. So we have purified the gases. We have compressed them to attain the required pressure. And now we have heated them to attain the required temperature. Now, the only condition remaining now here is now taking the gas to the catalytic chamber. Now we go to the next, which is now, we first of all, before we go to the catalytic chamber, we look at what the role of the heat exchanger. The heat exchanger is to heat the incoming gases. The gases we are talking about, the gases that are being heated are what? Nitrogen and hydrogen. So to heat the nitrogen and hydrogen gases and to cool the ammonia produced. So the role of the heat exchanger acts as both as a coolant, it facilitates the regulation of temperature. So it is also able to cool the product formed, which is ammonia, and also to maintain the reaction temperature, because we said it is the heat exchanger whereby we are able to attain that temperature of 400 to 500 degrees Celsius. So it is to maintain the reaction temperature, to cool the product, and also to heat the incoming gases. So in many times, many students give a very general and vague statement, like the role of the heat exchanger is to heat the incoming gases. That one does not make sense. If you're in the manufacture of ammonia, talk about to heat the nitrogen and hydrogen, to cool the ammonia, because that is the product that is found from there. Then now we have purified the gases, we have compressed them, and we have also heated them to acquire a particular temperature. Now we take them to the heat exchanger. Reaction at the catalytic chamber. Reaction at the catalytic chamber. So the gases have been purified. After being purified, they have been compressed, and now they have been heated to acquire the required temperature. So The raw materials are there, that is nitrogen and hydrogen. They have been purified. They have been compressed to attain the pressure of 200 to 500 atmosphere pressure. They have been heated to a temperature of, they have been compressed to acquire a pressure of 200 to 500 atmospheres and heated to the required temperature of 450. Now they are taken to the catalytic chamber. So all the conditions that are required have been achieved. We have the required pressure, we have the required temperature, and now the catalyst is there. So the main reaction now occurs at the catalytic chamber. This is whereby reaction occurs. So reaction occurs here, whereby the reaction takes place. The temperature is required between 400 to 500 degrees Celsius. So from there, the reaction takes place now, whereby we have ammonia gas. We have ammonia as a gas reacting with hydrogen gas to form 2 moles of ammonia gas. To form 2 moles of ammonia gas. Very important. 2 moles of ammonia gas. Very important for you to be able to capture that. These are gas. So now we continue and we go to the next point. We can now be able to go to the next. Now the reaction has taken place. We have formed ammonia. This ammonia, what is formed, is again taken back to the heat exchanger for cooling. From there now we go to note. The ammonia gas from the catalytic chamber is then cooled in the condenser to form liquid ammonia. Unreacted gases like nitrogen and hydrogen are recycled back. So that is very much important for you to be able to capture. So now we'll go to the flowchart diagram, whereby now we're having the other process, the schematic diagram. We have the hydrocarbon. The hydrocarbon is now forming ammonia. We have the hydrocarbon which is now forming ammonia. So the hydrocarbon, which can be like butane, is cracked to form hydrogen gas. We also have air, whereby through fractional distillation you get nitrogen gas. So we are able to get nitrogen gas through fractional distillation, and we are also getting hydrogen through cracking. So what that one happens is that now we go to the purifier, which occurs in the dust precipitator. So here we remove dust. We remove dust particles. So once you remove the dust particles, now here we have the purified gases. Purified. The gases are purified. So we now have purified nitrogen and hydrogen. So once they are purified, now they are taken to the compressor. At the compressor, they are compressed to around 200 to 500. Okay, I can use this. So at the compressor, the gases are purified. At the compressor, we are having now the gases being compressed to a pressure of between 200 to 500 atmospheres. So the gases are compressed now to attain the required pressure of 200 to 500 atmospheres. Then we are taken to the heat exchanger, whereby the gases are now heated to 400 to 500 degrees Celsius. So the hot gases, now here we are having, it is important to capture this. This is now the hot nitrogen and hydrogen gas. They have been heated now. They are taken to the catalytic chamber at the required temperature of 400 to 500. So the catalytic chamber, we are having iron mixed with aluminum oxide. The aluminum oxide acts as a promoter. So in that kind of a scenario now, we are having another arrow from the catalytic chamber back to the heat exchanger. And this now is whereby we are having now the ammonia. So the ammonia gas, because it's hot, is taken to the heat exchanger, which try to cool, because they said the role of the heat exchanger to heat to heat the incoming gas, which is nitrogen and hydrogen. So when they get to the here we have now the purified and compressed gases entering the heat exchanger. When they go to the heat exchanger, now they are heated to temperature over 400 to 500 degrees Celsius. The hot gases are taken to the catalytic chamber, because the reaction will always occur at a temperature between 400 to 500 degrees Celsius. So at the catalytic chamber, all the necessary conditions have been met. The gases have been purified, they have been compressed, they have been heated to acquire the required temperature. Now from there, we have the catalyst and we have the promoter. So reaction occurs there. So this is whereby the reaction takes place. The nitrogen reacts with the hydrogen to form ammonia. This is whereby the real reaction takes place. This is where the reaction occurs. This is where the reaction occurs to form the ammonia gas. Now the ammonia now taken to the heat exchanger for cooling, and then now the ammonia again is taken to condenser for further cooling, whereby now you have the liquid ammonia. Now here you have the liquid ammonia. In the condenser, the ammonia is converted to liquid, and now the liquid ammonia now we pack it for storage. If you're going to be able to see later, or rather in the chemical properties of ammonia, you remember that now ammonia reacts with sulfuric acid to form ammonium sulphate. Ammonia reacts with sulfuric acid to form ammonium sulphate. Ammonia also reacts with phosphoric acid to form ammonium phosphate. Ammonia reacts with nitric 5 acid to form ammonium nitrate, and ammonia reacts with copper to form copper plus water plus nitrogen gas. It's also another product that is formed there. So ammonia plus the copper oxide. Ammonia is a reducing agent, soluble to reduce the copper oxide to copper metal, and is now converted to water and nitrogen gas. So it's reduced to nitrogen gas. So in such kind of a scenario, it rather is oxidized to nitrogen gas. Ammonia will reduce copper to copper metal, but itself will be oxidized to nitrogen gas. The rationale is now the oxidation state of nitrogen in ammonia is -3, but now in nitrogen is 0. So the oxidation state increases from 0 it increases from -3 to 0, and that is oxidation. So the ammonia undergoes oxidation, but the copper oxide is reduced. So the property of ammonia being exhibited here is that ammonia is a reducing agent, or rather the reducing property of ammonia. So this schematic diagram summarizes the preparation of ammonia, all the steps, starting from the source that the hydrocarbon is cracked to form hydrogen gas. Air is freshly distilled to obtain nitrogen. The purifier, the gases are purified to remove impurities which would otherwise poison the catalyst. Then it is taken to the compressor, whereby they are compressed to attain the required pressure of 200 to 500 atmosphere pressure. Then it is now taken to the heat exchanger, whereby the gases are preheated to temperature over 400 to 500 degrees Celsius. Then the hot gases are taken to the catalytic chamber, whereby reaction occurs now. So then from there now we have the ammonia. The reaction occurs in the catalytic chamber, that is, as I'm showing here, that the nitrogen and hydrogen react to form the ammonia. Then now we have the ammonia is now taken back to the heat exchanger for some cooling. Then a little bit cooled ammonia will now be taken to the condenser, whereby it is further cooled to form the liquid ammonia. Then the liquid ammonia, this one is just showing you some of the properties of ammonia. Remember, the ammonium nitrate, ammonium phosphate, ammonium sulphate are used as a fertilizer. Very, very important to capture that. So uses of ammonia, we look at the uses of ammonia. Softening, add water, is used in softening, add water. Used in softening, add water. Is also used in manufacture of ammonium nitrate, or rather manufacture of nitrogenous fertilizer. So the statement that is captured in most of the books and what students read, like manufacture of fertilizer, is wrong. That is a very general statement. Talk about manufacture of nitrogenous fertilizer, or rather manufacture of ammonium nitrate, manufacture of nitric 5 acid, manufacture of hydrogen, which is used as a rocket fuel, as a refrigerant in large-scale refrigerating plants such as ships and warehouses. Very important for you to be able to capture those uses. And make sure that your uses are very clear. Sometimes we may even ask you to state the use of ammonium nitrate. Many students will say it is used to manufacture fertilizers. Ammonium nitrate cannot be used to manufacture fertilizer. Rather, it is used as a fertilizer. Very important. So we look at the revision exercise, and dry ammonia is passed over heated lead through oxide, and the product passed over an hydrous copper 2 sulfate as shown in the diagram. So we are reacting this. First of all, you need to know the reaction that takes place. When you pass ammonia over lead, the reaction takes place to form what? So when you have this lead oxide, so we're having now lead oxide here. When you react lead oxide with ammonia, the products are lead plus nitrogen gas plus water. Once you know that, then you'll be able to answer that particular question. So you try to get that two observations that is mainly the combustion tube. And remember the combustion tube, we have lead oxide and we also have anhydrous copper sulfate. Remember there is water here. This anhydrous copper sulfate, which is white. So when it reacts with the water, which is one of the products, it's going to change from white to blue. So you can say the white and anhydrous copper 2 sulfate changes to blue hydrated copper 2 sulfate. So the white anhydrous copper 2 sulfate changes to blue hydrated copper 2 sulfate. We also have the lead oxide. That lead oxide is usually yellow. So it changes to yellow to orange because lead oxide is important to capture this. Lead oxide has two colors depending on the state. So it is yellow. It is yellow when it is cold, and it is orange. It is orange when hot. So it turns, the lead oxide will change from yellow to orange and finally gray because lead metal is gray. It's always so important to capture that all metals are gray except copper, which is brown, and gold, which is yellow. So all the other metals are going to be gray. Also, it's not correct whereby some students talk about a silvery white. There is no color called silver. So silver, the color of silver is gray. So the color we are talking about there is gray color. So the lead oxide will change from yellow to orange and finally to gray. So the observation will be the yellow solid changes to orange and finally gray, and also the white anhydrous copper 2 sulfate changes to blue. The property of ammonia in this shown in this experiment is ammonia as a reducing agent. Ammonia as a reducing agent. Very important for you to capture that. So the answers are there. The yellow solid changes to orange, then gray. The white anhydrous copper 2 sulfate changes to blue. And the property of ammonia being shown in this experiment is that ammonia It is a reducing agent, rather the reducing property. And finally, after looking and after listening to my beautiful lesson, now I'm going to give you some assignment. And the assignment is name a suitable drying agent for ammonia and describe one chemical test for ammonia gas. Name a suitable drying agent for ammonia and describe one chemical test for ammonia gas. We have come to the end of our beautiful lesson today.